Hi everyone, this is the 2.3 video, which is titled Rate of Change and Slope. And through this section, we're going to discover the relationship between what a rate of change is and the slope that we compute with a line. So the first question that we're going to tackle is, what is a rate of change? And how is rate of change related to slope? So think about where you may have heard those words rate of change before. Maybe in a previous math class, maybe in a science class where you've done some applications with rates of change. And then how would you make the connection to slope? I'm going to have you formally define rate of change as this. A rate of change is a ratio. Now, what's a ratio? Ratio is a fraction, basically, that compares how much one quantity changes on average relative to the change in another quantity. You may have talked about this in science class before and talked about it in relationship to the dependent and independent variables. Rate of change is the change in, that delta sign means change in, the dependent variable in relation to the change in the independent variable. We can shorten that math-wise to think in terms of the change in y over the change in x. Remember, the y variable is the dependent variable, and the x variable is the independent variable. So how does this connect to slope? Well, the idea of slope that you've studied before actually is this change in y over change in x idea. The slope, if we think just mathematically, describes, and I put this in quotes because this is kind of the cheat term, the steepness of a line, and is found by computing the change in y over change in x. If you remember back from Algebra 1, slope is equal to y sub 2 minus y sub 1. That's our change in y. We need two ordered pairs over x sub 2 minus x sub 1. So this general idea, change in y over change in x, change in the dependent variable to the change in the independent variable, to the specific formula m equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1 will all come in handy as we go through and we do our work in this section. So if you have questions about just the ideas here or don't recognize the formulas, make sure that you write that down and ask me when you get to class. We're going to keep going forward here with this, and we're going to do an example that actually has a little science connection. It says the table shows the temperature of a solution after it has been removed from a heat source. Find the rate of change of the solution. So we defined rate of change as, remember, the change in y over the change in x, or the change in the dependent variable over the change in the independent variable. So if you remember correctly, this is our x column and this is our y column. Our left-hand column is the independent variable and the right-hand column is the dependent variable. So in order to compute this, we really need to just pick two values, two specific pairs. So what if I work right from the first two? If I work from this set of information and this set of information right here. the rate of change is going to turn out to be the change in the y's. That's going to be these two numbers subtracted from each other. So 139.4 minus 143.6 over the change in x. We have to stay in the same order. If I did 139.4 first, I have to do 4 first in the denominator, or 2 first in the denominator. 2 minus 0. That leaves us with negative 4.2. You can do that on your calculator if you want, over 2, which in turn gives us negative 2.1. Now we said a rate of change is a comparison. It's a ratio. So what is being compared? Well, it's negative 2.1 degrees Celsius for every 1 minute that's occurring. So this label comparison, this label ratio is also very important in your answer. So this is saying for every minute, we're going down 2.1 degrees Celsius when that substance has been removed from the heat source. So that makes somewhat common sense. In this problem, and you might want to do this independently for a second, see if the rate of change comes out exactly the same if you pick 2 other values in that table. If it's a linear function, it should. If it's not linear, the rate of change is going to actually vary. And that's what goes along in my statement here. Not all rates of change are constant. So this is important to know. You've studied lines really in depth so far and kind of brushed on parabolas. The rate of change in parabolas varies. If they vary, we often find what's called the average rate of change. And we're going to abbreviate that ARC. And I'm going to show you an example that's going to deal with something where we might use the average rate of change. So make sure you have this in your notes, and we will move on to the next slide. All right, I have a graph. The graph is a little bit hard to read when I put it up here on the document, so I'll give you the numbers a little bit more specifically here. But I ask you to refer to the graph. You notice a lot of these are application type problems. Refer to the graph below, find the average rate of change of the percent of total music sales for both CDs and downloads from 2001 to 2008 and compare the rates. So this value right here, this is the CD graph, is, let's see, 89.2%. And this value right here is 77.8%. So if we want to focus on the CDs this time, the rate of change is going to go, we want the rate of change of the percent. So the percent, remember, if we look on the y-axis, that's going to be our change in y. So I'm going to do 77.8 minus 89.2 over, now 77.8 correlates to the year 2008. So 2008 minus the 89.2 correlates to 2001, which is going to give me negative 11.4 over 7, which will be about negative 1.6% per year. So that means that the average rate of change has decreased an average of negative 1.6%. The negative is indicating that it's going down, it's decreasing. The downloads will probably be a different story, don't you think? Because that's the way music has kind of gone. This value right here in 2001 was 0.2%, just 0.2%. And in 2008, it went up to 12.8%. I wonder what those numbers would be now. I wonder if someone can get the statistics on that. So to compute the average rate of change here, I should have labeled this too. That was careless of me. Average rate of change equals. So average rate of change equals. We should always indicate what we're solving for. We're going to do 12.8 minus the 0.2 over the same years, because we're comparing the same span of years, and we'll get 12.6 over 7, which turns out to be approximately 1.8%. per year if you do that on your calculator. You should make sure that you can do these things on your calculator too. Even though I'm giving you the answers to them, you should try to do them along with me so that you get used to punching in the keys on your calculator. So if we compare these two, this one to this one, obviously one is negative, one is positive. There's a positive symbol in here. And the rate of change, the average rate of change, was a little bit faster for the downloads than the drop in the CDs. So something like that you could put into words as far as what you would use for your comparison.
With a teacher for extra help, would you please call 3?
Sorry for the announcement.
Thank you.
If you have any questions on how to either read this graph, like I said, the numbers are a little bit blurry, but those are the numbers that it's actually in your book. If you need to look at that further, let me know, and we can do a little bit more investigation. But something, analyzing a real world situation like that is not completely out of the question for you to be able to do on your own, especially for an assessment. We are on the last slide of this. This is going to be a quick little section. We made the connection in the first slide about the rate of change versus slope. Slope is more of a numeric computation that's used with functions in math. So slope and rate of change go hand in hand. Rate of change is more the application piece that we talk about. But slope, when I ask about slope, we're actually just looking at the change in the y coordinates over the change in the x coordinates for a function. So I'm asking you in this case to find the slope of the line that passes through 2 points. One is -4,3 and one is 2,5. So we know the formula for slope. M equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And we're just going to sub in. If you have trouble or think you're going to forget what's what, label x sub 1, y sub 1, x sub 2, y sub 2. So in this case, I'm going to say 5 minus 3 over positive 2 minus -4. That's going to leave us with 2 over 6, which is 1/3. So that means for every 1 unit we go up, we go over in a positive direction 3 units. So that would tell us that our line is going to rise to the right. So it's headed up in a direction like this, which tells us we have that positive slope. I think you probably remember that from Algebra 1. You have to basically be able to compute slope. They may be a little bit more challenging with decimals and fractions, but you just still apply the formula that's above there. The last one is going to be to find the slope off of a graph. So I'm going to graph something for you here. Draw yourself a coordinate plane. Put some tick marks on it. And I'm going to have it go through and look like this. So this is our y equals f of x. I'm generically calling it f of x because I didn't put a specific function name to it. Now, if you're doing this graphically, the best thing would be to pick 2 spots on your graph where you know that you've got actual whole number values for points. It's going to be this one for this graph and this one here. It may not look perfect on the smartboard or the way that you're drawing it, but we're going to use these 2 points. So remember, slope is change in y over change in x, or that y sub 2 minus y sub 1 over x sub 2 minus x sub 1. If I have a graph, I'm probably going to use this idea instead. So I'm going to pick a point. I'm going to pick one of the points that I just chose here, maybe this one, and I'm going to see how many units, how many tick marks I have between the point I pick on the y-axis and the other point. So I go up 1, 2, 3. So this distance is 3. And then I go, and I'm going up 3, so it's positive. And then I have to go over, because it goes right here, go to the left 2 in order to get to that other point. So the change in the y is 3 positive units, but the change in the x is 2 negative units between the points. So overall, my slope is -3/2. If we had gone in the other direction, because some of you may have said, well, I want to start with this point, I would go down 3 first. So I would have a -3 in the numerator, and then to the right 2, which would be positive, still -3/2. As long as one, either numerator or denominator, is negative, then the entire fraction is considered to be negative. So you should, in addition to being able to compute through the formula, be able to compute the slope off of a visual. If you have any questions on this, make sure that you write those down and ask when you come into class, and we can have a discussion and do some more problems together before I let you on your own to work on some of the problem sets. So thank you for listening, and I will see you in class very soon.